Suter from the Swiss team, and I'm going to present you a problem screaming balloon. So the problem states that if you put a hex nut into a balloon and you make it roll, you can make the balloon scream. And so we have to study the characteristics of the sound and find the important parameters. So here how it looks like. Here's the sound, so we have to study this. Now, I'm going to first describe the phenomenon, then study the frequency as well as the amplitude, find the limits of the model I do, and do some further investigations, and finally do a small conclusion. So here, here's a video of how the hex nut rolls on the balloon. Oops.
Well,
can someone play the video, please? So what we will see is that the hex nut, when it moves, it pushes the membrane of the balloon. And so how is the sound produced from this? So we can see also in the video that actually the hex nut is rolling without sliding. And so when it pushes the membrane, what happens is that you have air molecules that are pushed out. So you have uncompressed and then compressed air, which is a variation in pressure in air, which is basically what sound is. So this is the reason why we hear a sound from the hex nut rolling. So here's the possible important parameters we considered in this problem. So first, for the amplitude, we have the elastic properties, so the Young modulus of the balloon. Then we have the mass of the nut shape, as well as then the membrane thickness. Then for the frequency, we have the nut edge length L, the balloon radius R, the rotation frequency balloon, and then the nut shape and the side number of the hex nut. So here's the setup we used to do our experimental data. So we use a camera to film the balloon and to find the rotation frequency. Now we also use a microphone which has a flat frequency response to measure the amplitude as well as the frequency of the sound that is heard. So and then we rotate the balloon by hand here. So here's the model for our frequency. So the idea is that the frequency we hear because of the hex nut is due to the fact that the hex nut hits the balloon at a regular time, which is given by the ratio of the perimeter of the balloon over the edge length of the hex nut times the frequency rotation of the balloon. So now this is a pretty simple model, and we actually verified it. So here's the different edge lengths, and we can see that indeed in this case it is proportional to the side length L if we do it like this. And so for the radius it's the same thing. We also observe that it's proportional to the radius. And so if it only depends on the radius and the edge length L, then if we take different shapes but with the same edge length L for the same mass, we should expect that we actually have the same frequency of sound. And so we did this, and we actually see for that different exotic shapes, we actually do indeed have a similar relation. Now, let's push this theory a bit further and try this with a hex nut that is asymmetric. That is, one side is shorter than the other. So what happens in the balloon is that you will have the short side that will touch, and then the bigger side that will go, and again the short side, and then the bigger side. So what we should expect is like a tack, 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 tack. Right. So in this case, what we have is that the two edge lengths are more or less the same size, so the frequency is almost the same. And so what happens when you have two frequencies that are really close together is that you get beats. So you actually have an envelope frequency, but then also a frequency inside it, as the formula tells us. So now, here's a Fourier transform of such an asymmetrical hex nut. So we can see we have our two frequencies F1 and F2 due to the edge lengths L1 and L2. And we can actually see that there is the beat frequencies here, the two big peaks. But you can also see that we have smaller peaks in that case. What do they correspond to? Well, you can also see this rotation of the hex nut as one big rotation of a hex nut of size L1 plus L2. And this means you have another frequency that appears, and this is this one. And this one is a harmonic of this one. Now, if we look now at the amplitude model in this problem, so what we considered is that the membrane has an elastic force. And because the hex nut is rotating, it works against the centrifugal force. So now, if we can actually find the work we have to do against the elastic force, we can find the amplitude of the sound, because if the hex knot pushes more, then the amplitude will be more. So we suppose that the elastic energy is totally released into air pressure waves, and that we only have a negation for a small part of the balloon. And so what we get is that the work depends on the mass of the hex knot, the rotation frequency of the hex knot, as well as its edge length, and also the Young modulus. So that means, let's say we have a really, really heavy hex knot. Then the heavy hex knot will push the membrane a lot, so the amplitude will be really big. For example, also if we change the frequency rotation, then what happens is that the centrifugal force is bigger, so we have a bigger amplitude. Now, for the Young modulus, so if we have a big Young modulus, that means our balloon is really rigid, and so it will be really hard to work against the elastic force to create a big amplitude. And so in this case, we can actually see, so the amplitude squared is proportional to the work, because we do this hypothesis that everything is released into air pressure. So we actually observe this for the length. So you can see here we have the edge length for other constant parameters, and you can see the amplitude is indeed linear. And then what we did is that we inflated another balloon inside the first balloon to change the thickness. And you can also see that the thickness has has an influence on the amplitude. Now, another aspect which is important is that when you have a balloon, it has a cavity inside it. You also have air. So what you can see is that you actually have eigenfrequencies of the balloon. But there will be on one side the eigenfrequencies of the membrane of the balloon. But then you have a cavity resonance because there is air inside, so you also have these eigenfrequencies. And you actually can solve them using a pressure equation. So what you can do is either tap on the balloon to observe what are the frequencies, or you can also find it by doing a sweep in frequency on the balloon. And so be attentive, so on the eigenfrequencies you will see that the balloon is actually vibrating more than normal. Okay, and so now there's some limitations and some further improvements we can do on our models. So we didn't investigate a lot into the resonance frequency, but I will be really glad to discuss about it. Then we haven't tested experimentally on the Young modulus, so we should do some more experiments. Now the setup also has some improvements that can be made, mostly because we actually turned the balloon by hand. Also, one really important thing is that we considered that the balloon was a sphere, which is not the case, obviously, because the radius is smaller at the end of the balloon. And so this changes things, such as the radius, but also the Young modulus. So to conclude, we explained the origin of the sound in the balloon by air molecules being pushed by the membrane that is also pushed by the hex knot. We also give a model for the amplitude and the frequency for simple hex knot geometries. We investigated the important parameters such as the angle length, the radius, the Young modulus, and other more. We also pushed the theory a bit further by considering an asymmetrical knot, and we can see we actually have complex, a bit more complex behaviors happen. And finally, we also considered the resonance frequencies, both from the balloon and the air inside the balloon, which are also important parameters to consider. So the title was, we have a screaming balloon, and we can see in this case that we have a lot of frequencies that come into play, and that we have a really rich and complex number of frequencies in the problem, hence the screaming. Thanks for your attention.
So, hello everyone, I'm Martin, representing Team Chalmers, and I'll be proposing on problem number 9, screaming balloon. So, please, yes, we already heard the problem description. So, the percentage interpretation was that we were to study the characteristics of the sound, mainly frequency and amplitude, as a function of the important parameters, such as edge length and not mass and membrane thickness. Well, we start with the theory. They have a no-slip theory for the rolling of the nut, and they actually investigated it, which was nice. They considered the thickness of the balloon membrane and how it would influence the sound produced, mainly the amplitude, and they derived a simple formula to estimate the amplitude of the sound. Well, however, there were some flaws, or maybe with the theory, or rather shortcomings, such as they didn't quite investigate how the membrane starts vibrating when the nut rolls within it, and say how the vibrations of the membrane on one side influence the membrane on the other side through pressure differences. And they had sort of an ideal efficiency amplitude model. They didn't consider the damping from the air, and I think they considered the balloon ideally elastic. However, rubber suffers from hysteresis effects, so it's doubtful whether that is completely valid. And in the calculations for the frequency as function of the nut circumference, they didn't take into account the fact that the nut rolls inside the balloon, meaning that you get one rotation less per lap. So going on to their experiments, they used a very nice microphone with a flat response, which is important to be able to compare amplitudes of different frequencies. And they varied quite many parameters, and they say like they investigated the beats from an asymmetric nut as a slight extension of the problem, and they sort of investigated the eigenfrequencies as well. However, I don't think they used humans to shake the balloon, and I believe that the human factor might contribute to their very large error bars. And they also said that they routed the nut in a vertical way, which is not ideal, since that means that the speed may change due to gravity. And if I saw correctly, you kept the microphone quite close to the balloon, and the amplitude of the sound is dependent on the distance to the sound source. So therefore it might be better to keep it at a large distance, so that the small variations in distance when shaking the balloon don't affect the amplitude very much. They had their model with, let's think I'm running out of time. Okay, I'm not. Okay. They did not either consider that they said that the nut pushed the membrane, but they didn't sort of try to quantify how much it pushed it. Say, does a heavier nut push it considerably more, and thus change the relation between the period of the nut when it goes around one lap in the balloon and the frequency we hear. And I did not hear how they calculated the amplitude from the sound, and I didn't see any investigation of different nut speeds, which would have been nice. I believe that this is something we should discuss a little later. It might affect the amplitude, I believe, and for some reason they decided to use a Fourier transform rather than a power spectral density, which is considerably less noisy and therefore more appropriate to use when calculating, when finding peaks and calculating their width. So let's move on to the discussion. Have you some sort of validation for your amplitude formula, or is it just theoretical?
So we start the discussion?
Yeah.
Yes. So so we were only able to validate the amplitude formula for the edge length and for the membrane thickness. However, we did not show experiments on the young models and other data. However,
so you haven't verified it?
No, but however, what I did is that when you push the model to the limits, taking a high frequency or a high young modulus, it actually makes sense, as I explained.
Yeah, and then how did you extract the peaks? Because I think you had some sort of graph where you compared the the speed and the frequency.
So can you repeat your question?
You had some graph where you verified that it was the nut rolling that caused the sound. And then you compared the speed and the frequency, right?
Which are you talking about, the frequency?
Yeah.
Yes. Is it this?
How did you extract the peaks from the spectra? Did you just take the maximum, or did you do some sort of proper calculation?
We have made a measurement of the background noise and the measurement where with the X nuts rolling. We do the difference of the two spectrums, and we see clearly that we have one peak at one point, and this is the value that we take for the sound. And we have the error bar on the.
So you took the peak with the maximum height.
Yes.
Of the Fourier transform.
Yeah.
Which is very noisy. Won't this give you a considerable error?
Yeah, this one is very noisy because it's asymmetrical X-net, but before one X-net we have only one peak.
Okay. Yes. What you could have done to get a slightly more reliable estimate as well as an error estimate is to use the power spectral density instead. Then you take some appropriate windowing so that this very noisy signal becomes considerably smoother, and then you can get a better estimate of the peak position. And you can also then say calculate the quality of the sound.
Yes.
That is the width of the peak.
Yes, but there's actually a relation between.
Did you consider?
So there's actually a relation between a Fourier transform and a PSD.
Yeah.
But in our case, I think it was enough to prove our model. And in this case of the symmetrical hex nut, of course, you have a lot
wouldn't it have improved your model if you used the PSD?
I think the model would have changed. Maybe the data would have looked better.
No, they give the same thing, but the PSD gives it with less noise.
Yes, but I think we're still able to identify the peaks. Now,
yeah, but with quite some error. But now we should maybe move on.
You had a question about the membrane amplitude?
Yes.
Yes. So what we did was that you have your balloon here, right?
Yeah.
And so on your balloon, the membrane is vibrating.
Yeah.
So what you have is that you have like these oscillations on the balloon, if I draw them correctly, right?
Are these experimental or theoretical?
It's theoretical.
Did you consider the influence of the air
when
calculating these?
What I was saying is that you can see this, if we took it to a one-dimensional problem, then you basically have your different harmonics in the system. And what you get is that the wavelengths should be equal to the exact number of the length in the problem, which is about over I think it's Cn over 2L, right here exactly. And so what you have is that you have the resonance of the membrane, but you also have it of the air, right? Yeah. Because this is like a music instrument.
Did you verify it? Somehow experimentally?
No, we haven't. This is theory, and so the idea is that
it's some idealized theory which you haven't tested.
No, but we haven't done any plot on it, but we actually heard it when we did the experiment with the balloon. Now the idea is that this is like a bit of a music instrument, you know. So you have a resonance cavity of it, and then the air.
There's quite a large difference. The balloon membrane is a lot softer than, say, the resonance cavity in a guitar. It will vibrate very easily, and you are holding it, which affects it, and you're shaking it, and you have a nut pressing the membrane. I don't think such a simple model will describe the sound properly.
No, but so this is obviously a one-dimensional model, but the idea is that
one-dimensional model for a three-dimensional.
No, it explains the eigenfrequencies. So the idea is that if you only have the membrane vibrating, this is not enough to produce enough amplitude to hear it. Now, however, the air inside the balloon helps amplify these amplitudes by resonant frequency. So because
but you didn't test it.
Hello, one more time. My name is Olga. I'm from Team Ukraine, and now I'm a reviewer on the problem number 9, screwing balloon. In this problem, we were asked to investigate the hex knot rotation in the balloon and find how do the characteristics of the sound produced depend on the important parameters of the system. And starting with the report analysis, it was a very good report, thank you so much. And we observed the real-time demonstration of the phenomenon, which was very good. Also, the reporter described the sound generation quantitatively, and we agree with this description. Also, the reporter stated the possible important parameters which could influence the sound characteristics. And also, the reporter showed us a clear experimental setup. It was very good. Also, the reporter investigates a simple theoretical model, so he finds the main carrier frequency of the sound and studied the asymmetrical knots, which were very interesting. Also, the reporter studied the amplitude dependence on the parameters such as elastic properties and the mass of the knot, and obtained an eigenfrequency and explained it. But there are some weaknesses in the report. The spectrum wasn't studied theoretically, so the reporter find only the carrier frequency, and that's all. Also, the balloon was rotated by hand, and the time with which the spectrum, how long the spectrum they analyzed, you didn't state it. Also, interference from different points of the balloon wasn't studied, so it was just one point. Also, as the opponent said, the distance from the balloon to the microphone wasn't studied, and we didn't, in your report, we didn't see the experimental spectrum for hex knot, as I showed it in the verification question. And also, it was unclear if the position of the balloon was constant. About the position, the opponent asked a good clarification question about the wave rotation and about the different knot masses, which wasn't clear from the report. And opponent conducted a good deep analysis of the report and claims the importance of the distance from the balloon to the microphone. And however, the speed was investigated in the report, but the opponent said that it was no. And in the discussion, they discussed the amplitude and width of the peak. And the reporter claimed that he thinks that it was enough to study the phenomenon, but we still think that it was interesting to study spectrum also, and they discussed the membrane oscillation. Here I propose you to discuss the following discussion point. First of all, what was the period of time you used in spectrum analysis? What was the period? Also, are there some limitation for rotation velocity? And let's start and move on in the discussion because it's time. First of all, which period of time you analyzed to obtain the spectrum, and does it influence for somehow? First of all, you and then you.
So we have used 3 seconds. As we were shifting by hand, we decided to make a short time to see if it was constant or not. So we look at the data right after and see if it was constant or not. If it was not, we redo the experiment. So the spectrum is for 3 seconds.
3 seconds, and do you agree with?
I think that's on the lower end of what's enough to get a decent resolution in the frequency.
Okay.
Longer would have been considered better.
And how do you think the fact that we rotate the balloon also, does it influence or not? So not only the knot rotates, but also the balloon rotates.
So you mean in the frequency?
Yes.
Yes. So I think the amplitude difference from the sound from the hex knot is much bigger
Only
than the one you could hear from the rotation of the balloon.
So only the amplitude.
Yes.
So do you want to comment it?
I think the rotational velocity is very important since it partly determines, mainly that it determines the base frequency, and keeping it constant is important to get the well.
And about the superposition of oscillations, so the microphone detects the superposition of each point, and how do you think how it influences on the spectrum?
So you should have superposition oscillations, so the microphone should detect every frequency separately.
So if we consider not only one point that that rotate, that deflects and deflects, but all the points.
So we didn't do considerations on how the sound impacts the microphone.
Okay. And do you think it is important to take into account, but or not?
The superposition of
oscillation from different parts of the balloon.
so basically the directivity of the sound. It would be nice to take into account, but I think it would be very, very difficult to do so. So I do not hold it against you that you do not.
And again, if I might add, I think the effects are much more negligible in front of the model we proposed.
Yeah, and let's look at that.
Okay, and about the difference between the hand and the experimental setup, how do you think to the opponent
difference between the hand and the experimental setup?
Yes,
can you clarify?
Okay, we we rotate it by hand, and it may occur that from different position. We detect the sound from different position for experimental dependencies. So, for example, we start with this is the balloon, and when we analyze the sound, we start with this point, but in next experiment, the not at such position.
It should have quite a small influence. I think first 3 seconds. That's still enough for the balloon to go several laps around in the balloon, so that you could get a reasonable average. I think it's more severe that it might change speed if you rotate it vertically.
Okay.
Yes.
Okay. And
we actually did some calculations on how gravity impacts the velocity, and it impacts about 50 Hz difference, which is quite considerable, which is why we also have these peaks which are pretty noisy.
Then couldn't you have
sorry, it is time for the
but maybe just to add why we didn't do it like this, it was harder for us to do like this. We got just better results in 3 seconds something like this.
So it was less of a difference when doing it like this?
It was harder to experiment.
Let's ask the teams.
I'm interested in the same thing that they are talking about. So we have this problem with gravity accelerating on its way down when you shake it like this. So why not shake it like this?
Yeah.
Proponent and reporter.
Just because our setup, we have a bigger table, and so it was hard to measure like that with the microphone, so it was just practical, but I think maybe it would
again, but
we have done the experiment one time with like that, and we both studied the Doppler and gravity effect separately in both, and we have the graph.
Okay, and
you can actually look at the width of the peak.
So the width was smaller when you did it this way than when you did it this way.
You said it was more practical to do like this.
So I don't think this is very hard to do, and then you avoid the influence from the gravity.
But then again, I think this was good enough to show our model worked.
I think the opponent, the reporter said it in his point, and maybe other questions.
Yeah.
Okay. I have a question. When you said that when you rotated it, you shows the moment when the rotational path was stable. Do you think it's a missed phenomenon of when the nut rotates? The test shows moments when it only rotates in a stable path. Because are you certain? Because you found other things that it didn't rotate in a stable speed. I think that's why it shows only certain points. Do you think you missed some phenomenon there?
We could have the goal here was to show the frequency relation and also the amplitude relation that we did. Now, of course, if you rotate it, and also if it starts spinning in other radius, as I explained, the properties of the balloon change when you're on the radius. So, for example, you have a higher young modulus on the part that's more inflated and lower one on the one, so it changes.
Did I understand you correctly that the sound depends on where in the balloon the nut is?
I'm saying the amplitude, yes.
So it's different if it's here than here?
Yes.
Okay, I think that we have statement from the reporter team.
So yeah, can you please make some comments on the superpositional oscillation, because we'd like to move on.
Yes, I think that when we write this frequency, we only have the frequency of the 1 point. So, and if we would take into account on how the on the amplitude influences the way that from each point on the balloon the sound comes from each point on the balloon. So
I was asking to the opposing, actually.
On the superposition of the oscillations in the microphone.
No, for the hex nut that have different sizes. Superposition of different frequencies, because balloons.
Yeah.
For instance, if you take a hex nut of different sizes, what's your comment on what we did on that?
I think it was quite good. I think so. It was nice to see that
But maybe
you
if I
made
if I may say
extension.
something. So there are actually a lot of effects we actually neglected in our model because we stopped at the basic model for the main frequencies, also the eigen frequencies, which I think play the most bigger role in this problem, and that this is like effects that are really small and also harder to observe experimentally.
Yeah, of course. And the statement from the reviewer team.
Just a question for a reporter. What do you think what will change if you want to change the atmosphere within a ball, within a balloon?
So you change, for example, air for helium.
Yes.
Yes. So what happens is that you have the air also vibrations in the balloon that depend on what kind of gas you have inside it. So I think these frequencies would change. However, the frequency of the balloon, the hex nut rotating inside the balloon, is not affected by this.
And what about the width of these peaks? Will they change or not?
Maybe there is like resistance from the gas inside the balloon, which can affect this, but we did not consider this because we thought the effects were negligible.
Okay, and are there some limitation for the rotational velocity to observing the effect, for example?
You mean?
Yes, of course. So ideally, you would have something that rotates it.
No. If there are some limitations for rotational velocity, so.
Oh yes, you're limited by your hand.
Did you estimate this velocity or not?
Did we try to do it with the machine?
No. Did you estimate the velocity? For example, for this velocity, we hear no sound, so.
That might be.
The highest speed that we can and the slowest speed. I don't know the value by heart, but we have.
Yeah, let me if you want it.
Oh, okay, I see. It will be later because it's conclusions.
Thank you. And now concluding with the report.
Okay, so the problem we investigated was screaming balloon. So we offered an explication for the origin of the sound, as well as a first order model for the frequencies due to the hex nut. We also got the amplitude and also the eigen frequencies of the balloon. But thanks to the discussion, we were able to see additional effects that could enter in the problem, such as considerations of the power on the microphone, or how we spun the balloon. And for a more complete model, we could have taken that all into considerations. But in the end, I think it was a nice discussion. I would like to thank the opponent and the reviewer for that nice discussion, and thanks for your attention.
Good. Now questions from the juries. Please.
Yes, question to the opponent,
yes,
please. What influence do you think the rubber hysteresis will have on this problem?
Mainly that it will make it very, very difficult to model properly. So that.
But is there a qualitative difference to the sound?
It could be, yes, in that it may prevent some of the harmonics that the reporter discussed.
Maybe I could say, but I actually did a mistake by saying the harmonics were due to the fact that the edge length was longer. If you have a longer edge length, because you divide by the edge length, you should have a lower frequency, so my bad.
I think that it includes the amplitude of the sound, but not the harmonics and carrier frequency.
Okay,
Thank you. And maybe also, I think it's, as you said, really hard to take into consideration in the model. Yeah. Yes.
Please.
I have noticed that you investigated the eigen modes and eigen frequencies, but I didn't catch the role of these modes in the result. For example, if you have two different balloons with different eigen modes, eigen frequencies, but keep the frequency, the trajectory and frequency of nut rotation. will we have the difference in sound, and how could you describe this difference if
Okay, so what I would say is that what we observe is that the frequencies of the rotation of the nut and balloon has a higher amplitude. We heard it more. But when this frequency of rotation of the hex nut is close to eigenfrequency, then they have a really big influence. So if you change the radius of your balloon such that the eigenfrequency moves away from the frequency of the hex nut, then it has less influence than when it's close.
in what parameter?
Amplitude.
So you must see the variation of the amplitude as far as you change the velocity of nut rotation. Have you observed this variation?
No, we haven't. We only observed it. We only looked at it like this, and then we did some theoretical model, but not like you described.
Okay.
Thank you. More questions, please?
Yes, in your asymmetrical length measurement, you observed a tiny resonance at length 1, length 2, but a strong resonance at half the sum of the two lengths.
Yes.
Could you explain it?
So you mean beats?
Yes.
Yes. So we have our two frequencies F1 and F2 that are like really close together. And so what happens is that you have these beats with an envelope like this.
No, I mean
frequency.
Not directly the beats, but why it's F1 plus F2 divided by 2.
Yes, this is due to the fact that when you sum two cosines with frequency F1 and F2, you actually have a relation that is the product of the two cosines, one with F1 plus F2 over 2, and one with F1 minus F2 over 2.
But at the lower frequency, it was
F1 minus F2. Yes, and this is a really interesting effect because at first we were also intrigued, but actually what happens is that the ear is not sensitive to the phase of the envelope. So what happens is that you only think that you hear this instead of...
no, but you use a microphone, not easy.
Yes, but this is due to a thing of the pressure in the air. So it's important because of the pressure. So this is like mathematical. The F1 minus F2 is mathematical. But physically what happens is that it's only the pressure that the microphone measures, and this only measures F1 minus F2. But it's really interesting effect.
Thank you. Anything else? Please.
Can you please estimate the fractional difference of the velocity of the nut when it's at the top of the trajectory and the bottom of the trajectory?
For the reporter?
Yeah, to anyone who has an estimate perhaps. How much percent is the difference in the velocity?
Well, you said 50 hertz?
Yes,
roughly.
Can be a bit more, a bit less.
And then that would be like 10% maybe?
For
20?
Yeah,
so
it's
what
like
exactly
10%.
was 50 hertz? It was the difference in...
Yeah, the width of the
width.
peak,
Okay.
like half the width, yes.